Alright, so today we are talking about lesson 8-4 called the sine and cosine ratios. This has a huge connection to the last lesson on the tangent ratio, so it's similar mechanics. So if you understood that, should be doing okay here. If you did not understand that, then pay close attention because this will be a nice review. Okay. So first of all, what are these ratios? If we have two triangles, we should first be able to tell that these two triangles are similar because of the angle-angle similarity postulate. They both have a 90-degree angle. They both have a congruent angle as marked, which means they should be easily defined as similar triangles. And when you have similar triangles, that means all of your angles are congruent. It also means that all of your sides are proportional. So I can make a proportion with my corresponding sides. This side x corresponds with this side y. So I can say x over y equals, well, what other corresponding sides do we have? We have, let's go with this side m and this side n, also corresponding. So I can say that x over y equals m over n. It also equals, if I want to make the other side, the third corresponding side is this side p over this side q. Right? Those are my corresponding sides. So I could also say that this equals p over q. Now from here, you can, basic algebraic manipulation, you can see that if we are dealing with, for example, just this ratio here, m over n equals p over q. If you just multiply both sides of that by q and divide both sides of that by m, you would end up with q over n equals p over m, right? Which gives us a ratio on one triangle specifically, right? On one triangle specifically, where you have the ratio of the hypotenuse over the side, one of the leg lengths. And you could say, again, using algebraic manipulation, that the reciprocal must also be true. N over q equals m over p, right? Again, that's just algebraic manipulation. If you want to pause the video and kind of mess around with that, feel free to, or you can just trust me, or hopefully you saw it as I was discussing it. But you could do the same thing with x over y and p over q, and you would see that you can end up pretty easily with this ratio here. X over p equals y over q. And these two ratios specifically here are really important to us. And in fact, those are the sine and cosine ratios. So let's look kind of in depth at those. Let's start with the sine ratio. The sine ratio is defined as the ratio of the opposite leg to the hypotenuse on a right triangle. So we have triangle ABC here. It is a right triangle. So if I'm looking for the sine of angle A, and I'll tell you how to do the shorthand of this in a second. You don't have to write that every time. The sine of angle A, in fact, I'll just tell you now, is written as sine A, like so. It has nothing to do with sin or sinning or anything like that, so don't say sin A. If you've always wondered why your calculator has a sin button, this is why. It says it actually stands for sine. They just decide to use 3 letters for all of these. So please do not pronounce sin in your geometry class, because that is saddening for a geometry teacher to hear that. So sine of A equals, again, it says it's the opposite leg to the hypotenuse, right? So the opposite leg. If we're dealing with this angle A here, if we're here, the opposite leg to A would be the leg that is on the other side of the triangle, which in this case is BC over, with tangent we were dealing with the adjacent leg, but now we're dealing the sine ratio, we're dealing with the hypotenuse. So the hypotenuse in this case is the angle of the side that is not touching the right angle, which in this case is AC. Okay, and we'll look at an example, a specific example of this in a second. That's pretty cool, I guess. Well, I think it's cool, but I'm a math teacher, so that's how that goes. So let's look at the cosine ratio first. The cosine ratio is the ratio of the adjacent leg to the hypotenuse. And again, for both of these, we are specifically talking about right triangles. Okay, we're specifically talking about right triangles. Now, when we're talking about the cosine ratio, let's again look at the cosine of angle A. So the cosine of A. Again, we're looking at the definition here. It's the adjacent side, or the adjacent leg, specifically, to the hypotenuse. So the adjacent leg to angle A. I'm going to mark angle A here. The adjacent leg is the leg that is touching angle A. So we have two legs. Only one of them is touching angle A, and that's AB here. So we have AB over, again, the hypotenuse, which is here, AC. So let's look at a specific example. This will become more clear. Oh, I forgot about this. So this is the way to remember this in a good way. It's an easy way to remember this, I should say. This is a phrase we say so katoa. Okay, so katoa. So just means sine of, let's just say all these are angle A. Sine of A equals opposite over hypotenuse. Cosine of A equals adjacent over hypotenuse. And the tangent of A equals the opposite over the adjacent. So we have so katoa, so S-O-H, S-O-H, represented with sine opposite hypotenuse. So that's so. Then we have our sine, our cosine, C-A-H, which is represented with our cosine adjacent hypotenuse. So that's the ka. So ka toa, which again we talked about last video. The toa part is T-O-A, and that specifically is referring to tangent opposite adjacent. So this is just kind of a easy way to remember what goes with what goes with what. So remember that. All right, let's look at an example. If we're given this right triangle PRQ, we want to set up and look for a relationship between a couple of things. So I want to look at the sine of P, the cosine of P, the sine of Q, and the cosine of Q. And we're going to look to see if there's a pattern here. So again, sine of P, we're dealing with the opposite leg from P, so P is here, the opposite leg over the hypotenuse. So we end up with 9 is the opposite leg over the hypotenuse, which is 15, right? 9 over 15. And of course, you always want to simplify in math, so you end up with 3 over 5, dividing both by 3. Okay, now if we're dealing with cosine of P, let's get rid of this arrow. Cosine of P, cosine again means the adjacent, so ka, right, C-A-H, so the adjacent side length, which is 12, over the hypotenuse, which is 15, which simplifies to 4 over 5. What about sine of Q? Did I say Q? What am I talking about? Q is the right angle, so that's not going to work. My fault, guys. we're going to look at the sine of r and the cosine of r. Okay? Again, that's because we don't want to use q because it's the right angle, and this does not apply to the right angles in this circumstance. We'll get more into that in Algebra 2 and Trig. But sine of r, again, the opposite to angle r. So now we're dealing with this angle here, right? So the opposite of angle r is 12. So we have 12 over the hypotenuse, which is 15. And what does this simplify to? 4 over 5. Right? And cosine of r, which is the adjacent side length, which is 9. Again, so ka, right? So adjacent side length over the hypotenuse, which is 15 again, which is 3 over 5. So do you see anything that's the same? The sine of one of the angles, sine of p, is equal to the cosine of the other angle. All right? Is that true for the second angle we did as well? Let's look. We have the sine of r. Does that equal the cosine of p? It does, right? They're both equal to 4 over 5. So what do angle r and angle p have in common? Well, r is just 90 minus p, right? R is just 90 minus p. So we can generalize this by saying this. We can generalize this by saying that sine of x is the same thing as cosine of, in parentheses, x. Why am I using x? Oh, apologies. Sine of, well, let's keep the same letters, p, q, and r. Sine of p, or sine of r, equals cosine of p in this case, right? Sine of r equals cosine of p, but p is just what? 90 minus r. 90 minus r. And that's true in any case. Alright, that's true in any case. Anyway, that's just kind of a fun fact. So let's look at another example real quick. Again, we want an exact answer here. So if I'm solving for x and y, I've got lots of options here. Okay, we know this angle here is 35 degrees. So I'm going to set up a ratio, and I want you to kind of think of if you can think of a different way of doing this. So I'm going to say that, what are we given, first of all? We're given the hypotenuse, right? We're given the hypotenuse, which means using tangent in this case would be ineffective because tangent does not have the hypotenuse involved. Tangent is just the opposite over the adjacent. So we can use sine or cosine, either one, because they have the hypotenuse involved. So I'm going to use cosine, and I'll explain why. I can say that cosine of 35 equals the adjacent, which is x, over the hypotenuse, which is 20. Right? So to solve for x, all I have to do is multiply both sides by 20. So I got x equals 20 cosine of 35. Which again, you can type that in your calculator. Now, if I decided to use sine of 35, I would end up with sine of 35 equals y. Sine of 35 equals the opposite side, which is y over 20. That's solving for the other variable, right? So in this case, I'm going to, again, multiply both sides by 20 and get y equals 20 sine 35. And if you want exact answers, that would be them, right? That would be them. So those are kind of your options for finding exact. That looks like it's going to be it for part 1. So if you can continue to part 2, that would be fantastic.